sessions. First, we will have give a few minutes to each speaker to introduce themselves and say a few words about their talks. And then we will also go through the poster presentations, Ricardo Gomez, Sergio Joraz, and Alvin Joseph. And yeah, just to allow them to introduce themselves to the general audience. So Luca, maybe you can start. You should
okay, so I would like to share the screen. Is that possible?
Yeah, you should be able. Yeah, we see you.
All right. So good. I hope you can see it. Right. Yes. So very good. Thanks. So my talk is to discuss whether we can measure the geometry of space-time, which is essentially the background universe, in full and without assuming models of cosmology. So as you can see from what I wrote it down here, there are three quantities we need: h of z, h naught, and omega k. So these are, they completely fix the metric ground level. Now, I consider h naught is a well-known model-independent quantity because it only depends on the local universe. H naught in particular. The question is whether we can use all of them without assuming a cosmology, which is a bit different from what is typically done. Now, I need to clarify that when I say model-independent, I do not mean that I'm assuming some expand, because it's often used in literature in this sense, in the sense that of taking h of z or any other quantity and build a parameterization which is not based on a particular model. This is not what I'm talking about here. It's really not based on any parameterization. And also, when I say model independent, of course, I cannot claim that the one has to be or can be completely model independent. For instance, I will assume that standard candles exist. So in a sense, I'm assuming some model, but I'm not assuming a model of cosmology. So I leave it completely free, both at background and first order. There is another quantity, obviously, that we can measure from supernovae. The one mostly used is, of course, the luminosity distance. And when you see the expression of this quantity, you realize that essentially of the two remaining quantities, h of z and omega k, we just need another one because we can combine with the L. Therefore, the rest of my talk is essentially based on whether it's possible to measure h of z in a model-independent way, assuming that h naught and omega k can be measured, can be combined with other measurements which are also model-independent, like the luminosity distance itself. All right, so what's the idea? It's very simple. We do not measure only luminosity distance when we have standard candles. We can also measure the space correlation and the peculiar velocity. Now, in the linear regime, the peculiar velocity V and the density contrast delta are related by this simple expression that you can see written down here, which means if you measure both velocity, peculiar velocity, and density contrast, then you can measure a combination of H and beta, where beta is the usual expression, which is the growth of linear fluctuations divided by bias. On top of that, this is combined with other quantity like Z, which of course we can measure directly, and mu and k, which are the cosine of the direction angle, and they of course complicate a bit the calculation. But for the moment, just consider that we need to measure V and delta to get the product between H and beta. Now, on top of that, of course, we have to consider what is the variance associated with the supernovae, and if there is an intrinsic scatter sigma int, and if there is a nonlinear velocity attached to every supernovae, then you have a combination, the one that you can see here, derived a few years ago by Hu and Green and Davis et al., which gives you the extra variance on top of the measurement of the peculiar velocity. Now, what is left to say is that essentially we combine these three observables, which are the correlation of position, delta delta, the correlation of peculiar velocity, VV, and the correlation delta V. And these are the observable quantity. So the peculiar velocity is obtained simply because essentially the scatter you see in supernovae that are supposed to be standard candles is essentially the sum of the peculiar velocity, of the linear contribution of peculiar velocity, the intrinsic scatter due to calibration, and the nonlinear part. And we took all of them into account. So these are the three observables, and you see that beta enters in various combinations. In particular, it enters through the redshift distortion, the Kaiser effect. And that's why we can disentangle H and beta separately. So you can write down these three expressions and check which are the parameters on which they depend on. And you realize that essentially they depend on these 6 parameters: the luminosity distance T, the ratio E of E is just the Hubble function, dimensionless Hubble function is E, then beta, then some nonlinear velocity smoothing factor, and then the galaxy power spectrum. The entire three observables can all of them be written down in terms of these 6 parameters, and we do not assume any particular dependence on K or Z. You can measure them at every K and at every Z. So we're not assuming any parameterization, any model neither for E, nor for beta, nor for P, nor for anything. So you can measure this observationally at every, in principle, of course, for now, at every K, at every mu, and every Z. And there's a little complication that I discussed in the talk, but I don't have time to discuss here, which is how to obtain mu and K if you don't have already assumed the cosmology. So there is an extra complication there, but this is taken into account. And then the result is just usual Fisher analysis. We assume that there will be in a few years a survey like LSST, and taking everything into account, we're projecting on H, so marginalizing over all the other variables, we find that one can measure H with an error of 10 to 5% up to redshift of 0.5, 0.6. Of course, typically one assumes in this kind of forecast optimistic and more normal version of the experiment, and you can have various results. And essentially, we obtain the conclusion of this work is that we can obtain a measurement of H to some percentage of error, depending on various quantity, among which the most important are sigma intrinsic and the number of supernovae. So the final result is that we can obtain this quantity, the H of Z, sorry, up to a few percent, 5% or so. We actually have been pretty conservative in a few assumptions, so it could even improve. And let me conclude again, pointing out that this is totally independent of any cosmological model. So should not be compared with other methods, which of course could be more constraining, but will be less robust because they assume something. For instance, typically most methods assume that the space curvature is 0, and so they just have to invert the luminosity distance. Thanks.
Great. Thanks, Luca. So we move on to Mustafa. Please, try to keep it short so that we can you stop sharing? Yeah.
Yeah.
Well, you can see my screen.
Yes.
Okay, very good. Well, good morning, everyone, and thanks for the organizers for the invitation and organizing a nice meeting like this. So, testing GR, there are 3 methods to test GR. I talked about the motivation in my recording, but how to do that? 3 methods. So the first one is to use phenomenological parameterization. We put parameters into the equations, the perturbed Einstein equations, the growth equations, and we constrain them using some data. The second method is to go after some individual models and test them. And the third one is to, this is more recent, is to go after these inconsistencies and tensions between the data sets and dig into them. Maybe they're going to tell us something about gravity. For people joining the field or advanced graduate students, there is a review that if you want to look at the background. Okay, so I would like to, in this short summary, I would like to present the main results. And the first one is that with my student, Christian Garcia, we found that for the last 5 years, so we see that when we use only Planck, or Planck also supported by other data sets like BAO and RSD, we see that consistently, these 2 lines here that are the consistency with GR, so those lines come always like about 3 sigma or above, or more in tension with GR. So the data comes in tension with these lines for GR. This, if we put lensing data like CMB lensing or DES data, this tension goes away. This tendency continued in with the 2018 data. Now, we looked at, we said, what can we do with this? And we can fix one parameter and let the other one vary to see if we can gain some constraining power, or if we can dissect what's going on with this tension. The result is as follows. So we obtain that consistently here, these data sets here, if you can see the mouse here, I'm pointing to it with the mouse. So if this is Planck 18 and plus other data like RSD, BA, and so forth. So consistently in this plot and this plot and this plot, we see that this data is in over 3 sigma, in fact, 3.9 sigma tension with GR, which is the vertical line here. If we put at CMB lensing to it, we regain consistency to like about 1.5, so negligible. If we add DES data lensing, then the inconsistency, the tension goes away completely. So we do observe this dichotomy between Planck intention with GR, and then if we put lensing, GR is restored. Now, why is it so? Maybe some answer is in this fourth plot here, where we fixed sigma to 1, and we know that sigma is sensitive to the Weil potential, to the motion of massless particles. So when you put sigma, fix sigma equal to 1, there is consistency all over the board. But this is a work in progress. One other point I wanted to point to is that not only we observe a tension with GR, but also if we do a Bayesian model selection to see the preferences of the model. So you can see here on these 2 lines, you can see in these 2 lines here that negative here means it's favoring the lambda CDM GR. But we see that only when we fix 1 parameter, we get a little bit more power. So if we fix mu to 1 here, we see that in these yellow places here, we have some moderate preference, in fact, to the MG model. So, but again, if we put lensing data, that goes away. And also if we fix mu sigma to 1, this goes away. This goes away. So the question is why so? Well, the other approaches then we have is to go after some specific models, and we had some like FR, FG, and so forth. The difficulty is simulations. There are some good progress using COLA methods and emulators that can go very fast. In fact, COLA goes faster than n-body simulations, and this emulator goes 10 to the 6 faster than COLA approaches. So this is a promising thing. And finally, approach number 3. These inconsistencies and tensions, are they a sign of systematic errors that we go after, or are they a sign of some problems with the underlying theory? So this is to be pursued. And there was a lot of developments about quantities that can pin down and try to dissect these tensions. And I would like to say that we tried it for H0, for the obvious ones. We reproduced the results. We have something we call the index of inconsistency. And what I like about it is that the index of inconsistency is good at probing the overall volume of parameters to compare two data sets. And we do find, for example, here we do reproduce the tension between large-scale structure and CMB. In fact, we find a tension of over 3 sigma. This is the IOI, the index of inconsistency. And so this is consistent with other work, but those other work, they focused only on 1 or 2 parameters. We do it in the overall space. So this is to be followed and continued. So in conclusion, I did talk also about the binning methods of MG parameters that goes beyond the functional methods. Another result worth mentioning is this inconsistency or tension between GR and Planck, and mostly driven by Planck. And then the inconsistency goes away when we put lensing. And so there is some dichotomy. Also, to go after models, specifically emulators, are promising. So in sum, we do have some open questions, and there is a bunch of data coming in. So it would be interesting to see how this gets resolved. Thanks.
Great. Thanks, Mustafa. Martin? Can you stop sharing?
Do you hear me? Yes.
I didn't hear you very well.
You don't hear me?
You break down.
Okay, again. Yes.
It's better now.
Sound is better?
Yeah.
Okay, I can try to remove this if it's bad. Is it good?
It is working now.
Okay, sorry about that. I hope you can hear. So, hello everyone. I would rather to be talking to you face to face, but it's great that organizers still organize this great meeting and with this new format. So thank you. And I'll be talking briefly on two tests of cosmology with strong lensing. So strong lensing produces multiple images, highly distorted images of background sources lensed by a galaxy or a galaxy cluster. And this is the lens equation. So this shows the mapping from the real positions to the observed positions. So if you know this lens equation, you know how the multiple images appear, how they are distorted. And this mapping depends on the cosmological distances. All these distances from observer to source, observer to lens, lens to source are angular diameter distance. So they depend on the cosmological model. And also they depend, of course, on the mass distribution. This is a peculiar potential projected along the line of sight. So they depend on the mass distribution on the lens. So by using strong lensing, we can either constrain the mass distribution in the lens and or constrain these cosmological distances. So I will discuss just two examples of applications of strong lensing to cosmology. So one is a galaxy scale lens, and I will use a single galaxy cluster to constrain the cosmological distances. And a second example, you'll consider a set of galaxy scale lenses where we use the analysis to test modified gravity, like akin to the examples that Mustafa Ishak has shown. So this is the first application that we use this cluster, which has been previously used to set constraints on cosmological parameters by Gabriel Camin et al. So what we do here is that we consider a more extensive set of sources, so we are able to do a more detailed modeling of this galaxy cluster, and we are able to set constraints. In this case, we assume that we have a flat universe with a constant equation of state. So these are the constraints that we obtain solely from the analysis of a single cluster using strong lensing. And okay, there was a plot here, but I saved without animation. But anyway, we have a contour plots here on the space parameter of omega matter and W. And we overlay to them the constraints from supernova, BAO, and Planck. And we see a striking consistency of all these parameters. Although the error bars of strong lensing are larger, it's interesting that when combined with a single probe, strong lensing is able to improve the constraints on W and on omega matter by a significant fraction. What I find amazing, my code says I'm not sharing more. Are you still able to see my slides?
Yeah. Your image was frozen for a bit, but we could hear you. Fine.
Okay, good. I have to come back to my slides because I don't see them. Okay, that's Murphy's law. Let's see. Okay, I'll stop sharing and then go back. I think it's the best. So let's try to share again. Okay. Okay, as I find what I have to share. Okay, I think it's good here. Can you see my slides?
We just see a message that says that you started sharing, but we can't see your slide.
Maybe your connection is hanging.
Yes. Okay. Anyway, so I'll just speak without the slides, and once they show up, just let me know. But so it's rather striking that on the first, we find a good agreement with the constraints from other observables. So we don't find any specific bias by looking at this kind of observable using strong lensing. And still, it's although the constraints are broader than with the standard constraints, we are comparing, BAO with millions of galaxies and all sky CMB maps and thousands of supernova with a single cluster. So the next step is to run this on a set of clusters observed by the Hubble frontier fields, and then look at each one individually to see the consistency with other data, but also to combine them and to get stronger constraints. So this was on the galaxy cluster side. So now I'm gonna discuss the results that I have shown for the sets of galaxy scale lenses. So are you able to see my slides now, or not yet?
No, we can't.
Too bad. Okay. So anyway,
I mean, people should have seen.
Yes, I hope you have seen the talk,
yeah.
and then just go along. But okay, the talk is online. So we set constraints on the difference between the two scalar potentials of the metric in a generalized modified gravity situation. So that's the parameter eta that Mustafa Ishak has shown. So we constrain the psi over phi, so the ratio between the two scalar potentials in the metric, by considering data that is Einstein rings. So the radius of the Einstein ring is connected to the mass distribution of the lens, and we compare this to the kinematics of the lens, which is given by the velocity dispersion of the galaxies. So by combining this velocity dispersion and Einstein ring sets, we are able to set constraints on eta. And as I talk along, I'll try to make these slides appear because it's nice to see the plots, but anyway. But what we find with an analysis of about 80 systems, 80 strong lensing systems, is that eta is well in the interval compatible with eta being 1, which is generativity. So we find that by using the sets of strong lenses, we find an agreement with GR. And so this is consistent with what Mustafa was showing. However, we are looking at very small scales. So it's not a weak lensing large scales, it's strong lensing small scales. But still the constraints are in agreement with GR. Okay, so I'm trying to share again. And then next, what we do is that we use neural networks to try to measure these Einstein rings, to try to measure the parameter that we compare with the velocity dispersion to be able to set constraints on modified gravity. And so this neural network is able to make all the measurements we want, and we obtain a result that is consistent with what we put in the simulation. So we run simulation of strong lensing systems, we run a neural network to measure them, we compare with velocity dispersion, and we are able to obtain a value of eta that is unbiased with respect to the simulations that we put in. So I find this particularly promising with this approach, as we'll have a large number of systems in this ongoing wide field surveys. Then we can make a fully automated analysis from the neural network to find, measure, and then derive cosmological constraints. So sorry about all this problem with the presentation. For more details, you can look at the video that's recorded. Thank you.
Thanks, Martin. So now we give a chance to the poster presenters to introduce themselves. Ricardo first. Ricardo Gomez. Are you on? Ricardo. I don't see him online. So maybe Sergio, if you want to go next, then.
Yes. Can you hear me?
Yes.
Okay, good morning, everyone. So I'm Sergio Lloras. I guess I'm just supposed to present myself. So actually, I'd like just in a nutshell to tell that in our poster, we start in FFR theories. So instead of going from the effect from the Jordan frame to the Einstein frame and defining an extra scalar field, we do the other way around. And doing so, we arrive at a full thermodynamic interpretation of the scalar field. Actually, the third frame, if you will, to describe the instabilities of the system. It's really nice, full thermodynamic analogy. So please go to the PDF online to check for more details. Thank you.
Good. Thanks, Sergio. Albin, are you online? He doesn't seem to be online either. Okay, then maybe if they join later, we can give them a chance to introduce themselves. If not, then maybe we can open up then for the question session. So if you have questions, please raise your hand. And the participant list, I apologize beforehand if I am a bit slow at finding you, but if there are questions, please raise your hand now. Rogerio.
So I have a question for Luca. The error in the Hubble constant goes down as you increase the right. It looks like that in your plots.
I cannot hear. It was very.
Can you repeat the question?
Very broken.
Yes.
Connection cut, Roger.
Sorry. Can you hear me?
It's a bit broken.
Now it is better. Yes.
Try again.
Okay. Go for the next question. Sorry.
No,
go for the next question.
Now was good. Now was perfect. Try again.
It is working now. Yeah.
Okay, I was asking the following, Luca. In your plot, it seems that the error in the Hubble constant goes down as you increase the redshift.
Right.
Do you have understanding of why is that? And also in the fitting formula, it grows with redshift. It was like z to the power a half, if I remember correctly.
Right. So it's a point that Miguel doesn't like about the way I put things. So now you're reinforcing his doubts. So yeah, Roger, indeed, no, the first question is easy. It's the point that there are many more supernovae at high redshift, right? Because we are just taking constant slices. All right. And the formula, unfortunately, mixes a bit two things, Z and N. But N, as Miguel always reminds me, depends itself on Z. So it might be confusing. Now I realize that indeed it was kind of clear to me, but I see it could be confusing for other people, maybe more into the data. Anyway, so thanks for the question.
Thanks, Luca.
Okay, next question, Hideki Tanimura.
I have a question to Mustafa.
We can't hear you.
Okay. Can you hear me?
The volume was low.
Yeah, I could hear something, but very, very.
Okay. Is it fine now?
Yeah, it's better. Okay. I think it's better now. Yeah.
Okay. I have a question to Mustafa. You show in your first approach, you show the tension with TR in a parameter of mu and eta. My question is, do you see the same trend with if you use the WMAP cosmology, WMAP data, not the Planck data?
Yeah, it's a good question. I think the WMAP data is not strong enough to do for this. I believe we did that sanity check a couple of years ago, and we did not get contradictory results. Although we had less power, but I don't think we got anything contradictory. But we did check kind of 2 years ago whether we get something better with different with WMAP. But that was cluttered by the lack of precision, if memory is working here. Yeah, good question.
Okay, thank you.
Next question, Martin de los Rios. Yeah, Martin.
So from Mustafa, maybe it's been a question, but when you fit all these modified gravity parameters, you're also fitting all the other cosmological parameters, or you marginalize over them, you keep fixed? How it works?
Yeah, that's a good question. Absolutely, we fit all the parameters like the lambda CDM plus these two parameters, and we do include those parameters. We are doing a full fit in the full cosmological parameter space.
Okay.
It's like you take fitting the lambda CDM with the 6 parameters, and then fitting the lambda CDM, but then adding 2 parameters to try to represent deviations from general relativity, either mu and eta or mu and sigma, and do the fit, and then compare the not only what was interesting in this work when we fixed one parameter in order to get more constraining power. And what was interesting is that not usually we get tension up to 3 sigma, more 3.5. But what I found interesting to pursue is that this time we find that not only the parameters are in tension with GR, but also then when we go to model preferences using a Bayesian analysis, we find that in the case when we fix mu and we let eta, or in the other pair sigma vary, then we see that there is, in that case, there is a moderate preference to the MG model. Again, when we use CMB data and we reinforce it with BAO and RSD and supernovae. But if we put lensing into that, things go away. But yes, we do use the full parameter space.
Great, thank you.
Next question, Zakaria.
Hello, I have a question to Professor Ishaq. So it was a very interesting talk, and I have some questions about it. The first one, how do you explain that lensing make tension goes away? The second one, do you think that we could use these binding methods, for example, to these codes, or class codes, because there is a high class code for Hardensky theories? Do you think it's possible to modify and use these methods and implement them on these codes? The third one, do you think also it's possible to link the two methods using these generalized parameterizations and testing some specific models by using effective field theories, and like attribute this variation to each model, or it's not possible at all?
Okay. Thanks. Those are all good questions. If I can share my slide to answer at least 2 of these questions. Okay, so in this slide here, so your first question is why lensing restores consistency. Yeah. So if we don't include lensing, you see these data sets here, it's Planck and all others, except lensing. So here you have a tension, you add CMB lensing, it makes it worse. You add DES data, it makes it disappear. True for when we fix the parameters, when we let mu vary, eta vary, and sigma vary. But when we fixed sigma to 1, which is the GR value, so in this plot here, when we do that, we see that it goes away all over the board here. The tension goes away. So we did explain a little bit in this paper here that this can be related to the fact that Planck has difficulties into constraining correctly or in constraining sigma, but this is work in progress. So we don't know precisely why this dichotomy and why the CMB data or Planck 18 is in tension with these parameters. But we have a suspicion where we are moving to. That's the first question. The second question you asked about I think you asked about the binning. Binning method, yes. The binning method, we found it very useful because the binning method actually avoids the binning method. We don't have to specify. We don't have to specify a functional form. Some recent work showed that, including ours, there are some limitations. So the binning method, yes, you can implement it in high class. I think you do some not extensive coding, and you can easily implement it. Meanwhile, in fact, EasyGR is also available if you want to compare your results between EasyGR and class. But yes, it does require a little bit of coding. So and it's doable. The third one is, I think you asked about the EFT, whether you said the binning method and EFT, or you meant the other functional method and EFT?
Yeah, for example, just any parameterization, whatever it's functional or binning, and how to link it with some specific models of.
Oh, I see. You say yes, that's a good question. Yeah, okay. I think some work has been done on, for example, for Hordensky models. I believe a paper by Tisa Becker, where at the end they have a chapter where you can, in the quasi-static approximation, you can link the Hordensky parameters to the mu and sigma. So yes, there is, and then you can bin them if you want or not. So yes, there are links. That's the interesting thing, is that when mu and sigma are just parameterizations to tell you where there is some troubles, and when you find something, then from there you can see, okay, these values that are coming out, will they be in favor of f of r models, or this type of Hordensky model, or so forth. So it's a kind of a first approach to look for if there are problems or not. Once we find them, but probably we are not there yet because of the data in this moment. But that will be an exciting moment next, when we will be able to constrain them more precisely, more accurately.
Okay, so with which data you mean? With Euclid and so on, or?
Yeah, I think the first on the list. So we have Dizzy is coming soon, and then we have LSST, and then also Euclid and W first a little bit later. But yeah, LSST, Euclid, and Dizzy.
Okay, thank you very much.
Sure. Move on to the next question by Miguel Cuartin. Miguel.
Hi. So it's also a question for Mustafa. So if you can also share the screen if you want. But
sure.
It's slash question slash provocation. But for instance, if you go in your slide, I think 28, where you are testing the consistency between different data sets and different cases of mu, eta, and sigma, then you show lots of numbers, and then 28 anyway. So you mark then in yellow 4 numbers there. Yeah,
sure.
So you see, but if you look at, let's say, so many numbers, so many cases, so many combinations, you are bound to find some which are inconsistent just by random chance, right? Because if you look at, it's what people sometimes call, p-hacking, or so. If a posteriori effects, like you look at some combinations which will be, in intention just by a fluke. So how you think this could be the case or not? And if not, why not? How do you consider this case?
Okay, sure. Good. It's a good question. So I think however, here when you look at this table here, it's systematic. It's not like random in a sense that if you look at this whole line here, the first line, and then you look at the second line here. So you see that consistently, this is all negative, and this is all negative, and sometimes actually in the strong or in the moderate regime. So when we vary the 2 parameters at one time, so we find that there is tension. We see that there is about 3.4 or 3.5 sigma tension. However, consistently, the lambda CDM is preferred by the Bayesian analysis in these 2 lines here. And then, however, when we fixed eta to 1, nothing happens consistently. Okay. However, when we fix mu and we let eta and sigma vary. So we do have and again, because that's why it's a two-dimensional table. It's not only to look in this direction, but it's to look in this direction, what's happening as well. So we see that if we use only Planck 18 plus other things, and Planck 18 with other things, so we do see that there is a preference here for this model, the modified gravity model. It is a moderate preference, but still interesting. Now, however, as soon as you see we put CMBL, we put DES, we put DES, CMBL, DES, as soon as we throw in lensing, the preference goes automatically to lambda CDM. So so it doesn't look like there is any type of randomness here, but it's rather systematic. But it's a good question to check, and we can check it on this table, and it seemed to be systematically indicating when we don't use lensing and we use Planck 18 and we reinforce it with others, so, and we vary only one parameter, the preference does go to a modified gravity model. Yeah.
Okay, next question by Nelson.
Thanks. So I also have a question for Mustafa.
Okay.
So I was wondering on the simulation side, because you mentioned that you use, I mean, people are basically making emulators for simulations of modified gravity, but since you are
cutting, Nelson.
Hello.
Yeah.
So since you're using this parameterization for modified gravity, I was wondering if those parameterizations are also well simulated, and well, that's basically the first question. If you have simulations for this range of parameterizations that you have, and the other question is whether the nonlinear predictions from simulations are robust across different groups doing this type of simulations.
Okay, very well. I think, yeah, you asked two good questions about simulations, indeed. So the first one is, I think that's an excellent idea, project to. So what is happening now in the field is rather this: taking F of R models and doing simulations for it, taking Hordensky model and doing some simulations for it. There is not yet a successful simulations to, for example, do mu and sigma. I started maybe 2 years ago. I started the project with a student to try to do a simulation, just simulation, and then when you have mu and sigma parameters. That's an excellent project that tries to be done. So we started it, but we got slowed down because you need to have a formalism to embed into the simulations. We started with some formalism. You need the formalism that's actually can take you towards the nonlinear scales, and so that's a good thing to do, and I think that's something that is needed in the field. I started with a student. We got slowed down, and it's something that needs to be done. Good one. The second question that you asked, I think, whether there have been some comparison between simulations of. Now we're talking about, this is specific models like F of R or things like that. There is what is called the MG Halo or MG Halo Fit or something like that by Gongbo Zhao. I do not, and so there is also COLA simulations. Yes, COLA simulations were compared to full-blown up simulations. And in fact, in the emulator project that I worked with Giorgio Valogiannis, and we found consistency. So the answer is between COLA and N-body simulations by Bao-Juli, those were consistent. But there is room for more work in the COLA, because it's like to how scales you want, how far you want to go in the small scales and so forth. So This is the current status. Yeah, good questions.
Thanks. Claudia Escocola, next.
Hello?
Yeah.
So, can you hear me? Yes.
Yeah.
So this is a question for Luca. I want to be sure if I understand correctly. So when you talk about model independence, are you saying, you explained it, but I want to see if I understand. You referred to the cosmological parameters, or you are still considering general relativity and homogeneous anisotropic background on top of what you put expanding universe, of course, but on top of that you put the perturbation, or you are more general than that?
It's more general than that. So of course I'm assuming homogeneity and isotropy plus perturbations. So in that from that point of view is true, except actually the model could be applied also to, I guess also to like bubble scenario, something like that. But certainly we do not assume general relativity. It's really more general than that. We only assume that there exists a background metric, there are linear perturbations, and there are standard candles, and where there is a continuity equation between conservation of energy, or continuity equation between the velocity and the density contrast of sources, and that's more or less, that's what there is to it.
Okay.
So we do not assume GR, definitely.
So the equation between the metric and the tensor, and it could be anything.
Absolutely, yes.
Okay.
Correct.
Thank you.
But, okay, yes, I shouldn't start. Also, how you, maybe Renan, maybe I can also ask a question at the end. Renan?
Yes, my question is for Mustafa. And maybe it is a naive question, but yeah. In the approach 1, are you assuming GR to make these measurements, in the sense that I don't know exactly how are you making these measurements, but for instance, for redshift space distortions, are you assuming GR for computing the power spectrum, for instance?
Yeah, that's an excellent question as well. Yeah, I think actually many years ago, I think the community, first of all, I should say that I do not make measurements myself. I use the measurements that are made available by my colleagues working in on observations and so forth. We do go through the observation, through the catalogs, we analyze, we look at them, we do sanity checks and things like that. So I think it's a very good question, and this is very good. You want to know whether already in the data there are some assumptions about lambda CDM or some GR models. So in that case, I think the folks working on observations and data analysis have tried to not do that. This was done in some data, I think, for I don't recall, I think maybe supernovae or something. There was an assumption of lambda CDM at some time. Those have been, there is a great effort to get those removed. So I do not think that the data we are using in general has assumptions of GR lambda CDM, but maybe that's my understanding. That's my but it's a good question. So in other words, yeah, it's this is actually a problem that the community working on observation and data analysis are aware, and they try to not assume GR, not to assume GR a priori, if that can answer your question. But it's something that should be reinforced, and I believe that's the case in this moment. Yeah, good question. Mm-hmm.
Miguel, you have another question? Yeah.
Yes, but if you have a question, Bruno, I can go to the end because I asked already.
That's fine. Yeah, let's go with your question.
Okay, so anyway, for Martin, I was trying to understand better your deep learning. What exactly are you using? How many features are you using to train your deep learning? Because you say you're only using photometry in 3 bands. And so what are the features that enter exactly in your deep learning? And is the output only these 4 parameters that you have, theta e, sigma v, and the redshifts?
Okay, so this is a convolutional neural network which has been used. So what we trained actually is the postage stamps of the images of these systems. So they are trained on the simulations. So it's the full image that is trained in the 3 bands, and then we recover 3 parameters. So this is this machine learning approach we take from a paper by Clesio and al. So he's maybe online and can comment. So we just use their result for that. But so they recover the lens redshift, the source redshift, the velocity dispersion, and the Einstein ring angle. So they either choose only one of these 3 variables to recover, or they also train with the 4 sets, the 4 variables as outputs. But in any case, what we use is the velocity dispersion, which is the geometric velocity dispersion that we compare to the kinematic one. So yeah, I don't know if this.
No, yeah. That answers my question. So, but just okay. So, if you have only 3 bands, you have bad photo Z's, right? That's what I'm saying. So you don't have the and so how much could this improve if you get better redshifts? Okay.
So this is something we are willing to understand better. Of course, the source redshift is very poorly recovered. The large error bars, lots of outliers. The lens redshift is not so badly recovered, and this is not so surprising because these are early type galaxies, so it's a peculiar type of galaxy, which with 3 bands you can have an idea of redshift. But still, you have outliers, and I don't know the numbers. I can look at them, and the quantity that's really well recovered with less than 10% outliers and with an error less than 10% is this geometric velocity dispersion. So this is something we want to understand better. If it's like by miracle that the uncertainty in the other parameters, they combine in such a way that we have a small velocity dispersion, or if there is something less physical of the simulation that we are just recovering something that was put on in the simulation itself, right? So one of the things we want to do is to run these on different simulations and so on to understand how we get this sort of miracle combination of our quantity.
Thank you.
Bruno, yeah.
Hi, thanks for the speakers for the nice talks. My question is for Mustafa and Luca, or Mustafa or Luca. It's kind of a, I guess, literature question a little bit, because I'm probably missing some papers that might have done this. So it is about the parameterization issue. So Mustafa, in your talk, you very clearly talk about one extreme, which is choosing specific specific model, and then you have parameterization. The other extreme is freebiening for K and Z. But this neglects correlations and the strict model priors that you might have. There's possibly a middle ground, I guess, where I'm familiar with papers from Elgasem, and I think even Luca is a co-author in a paper where you could try to use Gaussian processes to try to constrain your redshift distribution of a given function in a way that is molded by the data, but that still takes correlations into account. I think there's a paper by Marco Raveri, if I'm not mistaken, where he tries to do a non-parametric sampling where you're simultaneously sampling the parameters of the models, but you're also at each step of an MCMC sampling the model that you're going to use among a family of models. I guess my question is, where are we in terms of trying to find a middle spot? Where is the field in the explorations of this middle ground where you try to add some complexity, but that is still informative to a certain extent? And whether we could try getting inspiration from some of the photo Z work that Alexandra described, where you're trying to use simulations to calibrate, to use as priors for non-parametric descriptions. And maybe that's similar to an emulator approach, but where you could try to do it with simulations of different models all at the same time. I don't know, I'm just kind of brainstorming ideas in the middle. I've been thinking about this for the past month or so, and I haven't really gotten anywhere. So I guess my question is, you know this much better than me. Have you gotten further than me? And what do you think about these things?
Remember that you have to answer in 2 minutes.
Sorry, yeah, maybe it's a big question. I'm sorry.
I can give it a shot if Lucas wants to go. That's fine too. Okay, I think what I gathered from your question is, if you worried about correlations, I think that now the way to do things is that you assume a model, then you have the parameters, and then it's good so we constrain the parameters, but we do also take into consideration the correlations between the parameters. And so that's taken into account when we do the work. So, and if there are also systematic effects, we put them in the analysis. The method that you mentioned by Raveri, for example, where he used the parameters, but also takes the models into the sampling, that's different. What is done classically usually is that to do the constraining the parameters, looking at the correlations, and then after that doing a Bayesian analysis to see which model is favored. I do not know what are the advantages of, for example, sampling at the same time the model. So it's an interesting question. And I think this is how I understood your question. If you are thinking of something more than this, like to arrive with it's good ideas are always welcome in the field. So, but as far as the current status of doing things, and I think this is how parameter constraint and correlations are dealt with in model selection and so forth. That's my take on this, on your question from my side.
I'm afraid that we will have to end the discussion at this point, and we thank all the speakers for the great talk. Luca?
I cannot answer because the question was also for me. It's too late.
Yeah. Okay, yes.
It's too late, just tell me, don't worry. I mean, I don't have to. Can I? So?
Yeah.
I think people can leave. But yes, please answer, Luca. Yes, I guess,
Okay.
right?
Thanks. Good. So just be quick. So my only take about this is that I really would like that whenever we write papers, we clarify very well as much as possible the assumptions. For instance, Gaussian processes, my impression is that it's really oversold. I mean, people claim that it's kind of model independent. Sorry, I don't agree. Although I've been an author myself of a paper on that, and I try to compare with other tools, with other methods. And I think people should clarify that there is plenty of assumptions, kernel, and things like that. So, and the Gaussian assumption per se is itself an assumption. So my only take is that I really would like that we pay a bit more attention on what are the underlying assumptions every time we use a method. If binning is the only thing that you need to use, like in the method that we have been proposing, then that's an interesting approach, and then that can be clarified very well. You just say I use binning, that's all I need to use. And you can also include all the correlations. It's not true that using binning you discard correlations. They actually implicitly assume in the method, for instance, we are using, and so on and so forth. So my only take is that whatever is your idea, a model, a specific model, a range model independent, whatever, let's try to be more clear about what are the underlying assumptions at every step. Thanks.
Great.
Okay, thanks.
Any final comments or thoughts on any of the presentations? Great. Then we thank all the speakers, Luca, Mustafa, and Martin. Great presentations. And yeah, so we end the session here. Yeah, I can clap.
Thank you for the speakers.
Thanks.
Thank you, everyone.
Thank you. Thank you, everyone.
Bye-bye.
And
See you guys in the afternoon session, 2 hours.
Yes.
Those who can make it.
Bye.